Hey, welcome back to Fan Mama Physics. This is a continuation on the unit of graphing, and in this video we are going to talk about matching equations to their graph counterparts by figuring out patterns, using patterns to figure that one out. So for this lesson and the next upcoming one, I'm going to have it in, I'm going to do two copies, two versions, because some of you may have learned the slope y-intercept form, and if that works really well for you, then I am going to, the other kind of matching video that I have with this one is going to do all of these problems by using this other method, which I think makes more sense, and it's definitely more applicable. But of course, your math teachers, senior math teachers, might think otherwise, whatnot. So I will also go over the basics, and also just to build pattern recognition for as a skill, because it is very important in math. So yes, I did say I was going to introduce a board game at the beginning of every lesson. This one I have here is Hanabi. It is a co-op game between 3 to 4 people. 2 people, not so great. It probably says on the box somewhere. But this is a logical deduction game, in fact. And but you might be thinking, what? It looks like fireworks. How does that have anything to do with that? Yes, Hanabi, if I'm correct, it is a it means fireworks in Japanese, I think, or festival. Or I'm probably wrong. Anyways, you get the idea. It looks very festive. Looks like fireworks, and that's exactly what you're doing in this game. Is you're trying to make fireworks. So how do you make these fireworks? You might, here I have a deck full of different colors, from blue, and there's green. I actually just took all the green cards here. Green, and I think, yeah, blue, green, red, yellow, many different colors. I think there's 5 of them. So anyhow, what happens is that as a team, you're trying to make fireworks. So what does that look like? It means that you have, these numbers go from 1 all the way up to 5. To make a successful firework, you have to place one card on top of the other in the correct order. So, for example, the 1 card for green has to be played first, then the 2 played second, then third, 4th, 5, and etc. If you play them out of order, let's say 1 was on the board and someone played a 3, then you screwed up. Basically, you lose some points, or you lose a set of fireworks. I forgot exactly the rules for that, but anyways, that's the idea. And it might sound very easy, but the added trick, the added layer of difficulty comes to the fact that whenever you get your set of cards, you have to show them to everyone else on the team except yourself. So you don't know what cards you have. And when it's your turn, you either have to give a clue to someone on what their cards might be, or you have to select a card and play it. And if it matches the pattern that is on the table for the fireworks, then you successfully played it. But if it's not, then you lose something as a team. So that is something to be careful with. So let's say I have these cards out like this. I don't know what they are, but I have a red 4, green. Sorry, I don't know my colors. A white 1, a blue 5, and a yellow 1. Okay, so these 2s are 1. So someone on their turn might tell me, oh, these 2 cards, they would have to point to my 2 cards and say, oh, these are 1s. That's a clue, okay? And now that I know these are 1s, I know when it's my turn, I can play them carefully and successfully, because we always start off with 1 and we go up in successful order. So someone might tell me, oh, this is a red color. They might tell me, oh, this is red, okay? Someone might tell me, oh, this is a 5, and usually there's only 1 5 in the game for every color, and you don't want to discard these, because if you did discard them, then you lose that opportunity to go up to a level 5 firework, which is less points for you in the end. So essentially, that's the idea. Is that there's matching involved. You have to match based off the pattern that you see, what people are giving you, and that is Hanabi. It is a very fun deductive logic game. Play cooperatively between 4 players is the best. It's just a small box, as you saw, which is great for when you're traveling around. It's a good small box to carry with you. Okay, so on with this lesson with matching equations to their graph counterparts. We have three graphs that you see in front of you, graph A, B, and C, and these three equations over here. So the first thing that we're going to do is we're going to take each of these equations, we're going to make a table of values, and we're going to basically see whether these values, these coordinates that we generate from this equation, matches any of the graphs that you see up here. If there is a match, if the coordinates do match, we know that this equation matches that graph and not the other two graphs. So that's the strategy that we have for the basic strategy for this particular matching equation to graph set. Okay, so let's get on and let's do the first one together. This one, okay, so I'm going to zoom in. I have y is equal to 3x plus 3. That is my equation. So what I'm going to do is I'm going to take this table, I'm going to generate some values here. It starts off with 0, 1, and 2, but you can use whatever you want to generate your table of values. You can use x is equal to 2, x is equal to 4, 5, whatever. But guess what? 0 is probably easy because guess what? If I put x is equal to 0 here, 3 times 0 is 0, then y is just equal to 3. That's pretty easy. And 1s also are very easy to deal with because 3 times 1 is just 3, and 3 plus 3 is equal to 6. Okay, next one, I have 2. 2 times 3 is equal to 6. 6 plus 3 is equal to 9. So there's my table of values. Okay, so now that I have these coordinates, I'm going to look at the graph and see if I can find a matching one that contains my coordinates. So let's check this first graph, graph A. So if I go to 0, x is equal to 0, do I get y is equal to 3? Okay, oh hey, I do. Okay, I do, but let's keep going. We don't know yet. Okay, if x is equal to 1, then my y is equal to 6. So my next point should be up there. Wait a minute. This graph doesn't go up, it goes down. So it can't be A, okay? So it cannot be A. Not A. How about this graph B? Well, we definitely know it cannot be graph B because it's missing this point and it's missing the other point that we mentioned earlier, so it cannot be graph B. It must be graph C then. Well, let's take a look. Check. Okay, at x is equal to 0, my y is 3. Okay, that's good. At x is equal to 1, my y is 6, which is, hey, is up there. Okay, it's working out. Yes, and then x is equal to 2, then my y must be 9. Okay, so that's a check right there. So that means, okay, where am I going to put this, put the answer here? Okay, so I'm going to put it right there. The corresponding graph that matches our first equation is graph C. So graph C is used up, okay? So we have the remaining two graphs to figure out. Hey, guess what? I think I'm going to give that task to you to do. What I'm going to do is, here, I'll show you the table of values, okay? And then I'll show you the three graphs A and B. So your task is to match the remaining equations to graph A and B. First one is x plus y equals 3. The next one is y is equal to 3x minus 3. I'm going to give you a chance to pause the video to try it out. Okay, now it is my turn to do so. Okay, so here, for number 2, I'm going to generate my table of values. When my x is equal to 0, my y is going to be 3. When my x is equal to 1, so I have this, I subtract 1 to the other side, so y is equal to 2. If I have x is equal to 2, 2 plus y equals 3, and I subtract 2 on both sides of the equation, I get y is equal to 1. Okay, so let's take, well, we know that if we figure out the one graph, we know by default the other graph must be the remaining by process of elimination, but for the purpose of more practice, I'm just going to quickly generate the values for the last set of tables, the set of equations, last table over here, okay? So 0, 3 times 0 is 0, so y is just equal to negative 3. Okay, what happens if it's 1? 3 times 1 minus 3, that is going to be equal to 0. Woohoo! All right, if I have 2, 3 times 2 is 6, minus 3, it is 3. Okay, so those are my values. Now I can take a look at which graph represents each of them. Okay, so let's point a few things out. Okay, so let's check this first graph. This first graph has when x is equal to 0, my y is 3. So that checks off. If my x is 1, my y is 2. Oh, hey, it's starting to check out. If my x is 2, my y is 1. So these 3 points fulfill this graph here. Therefore, my second equation, the match would be graph A. Now let's take a look at example number 3. I start off here at x is equal to 0, which is, down here. And it makes sense because my y is negative 3, which is exactly that point. If I have x is equal to 1, my y is 0. Hey, that checks off too. If my x is 2, my y is 3, which is up here. Okay, good. So absolutely, graph B does definitely check out, okay? Okay, so here we are. This is what it looks like to match an equation to the graph. You just have to figure out a table of values and then do those coordinate points fit the graph that you have in front of you. Okay, so this is the kind of the trial and error method to figure out which graph is which. The next video I have more examples, I believe, but I'm going to do the flipped version of this one where I'm going to do exactly the same. I'm going to have exactly the same end goal, which is matching the equation to the graph, but I'm going to do it in a different way. So stay tuned for that. Thank you for watching. Fan Mama Physics signing out.